Now the next question is, if a sequence Sn is defined by Sn equals S upon 1 plus Sn minus 1, where S is greater than 0, S1 is greater than 0, and N is greater than or equal to 2, then show that the sequence converges to a positive root of the equation x square plus x minus S equals 0. Now, if S is greater than 0 and S1 is greater than 0, then any Sn will be greater than 0. Now 1 plus Sn minus 1 will be greater than 1. Then we can write 1 upon 1 plus Sn minus 1 will be less than 1. And if we multiply it with S, we can write S upon 1 plus Sn minus 1 will be less than S. So any Sn will be greater than 0 but less than S. That means this sequence, it is a bounded sequence. Now we'll prove that the sequence is a monotone sequence. Now what we'll do is we'll find Sn minus Sn minus 2. Now this one will be S upon 1 plus Sn minus 1 minus S upon 1 plus Sn minus 3. Now we can write this as S plus S into Sn minus 3 minus S into Sn minus 1 upon 1 plus Sn minus 1 into 1 plus Sn minus 3. Now this S and S will cancel. So we can write Sn minus Sn minus 2 will be equal to S into Sn minus 3 minus Sn minus 1 upon 1 plus Sn minus 1 into 1 plus Sn minus 3. Now we can write this as minus S and then Sn minus 1 minus Sn minus 3 upon 1 plus Sn minus 1 1 plus Sn minus 3. Now if we simplify Sn minus 1 minus Sn minus 3, we'll get S square Sn minus 2 minus Sn minus 4 upon 1 plus Sn minus 1 1 plus Sn minus 3 1 plus Sn minus 2 into 1 plus Sn minus 4. Now if we look at this result, Sn minus Sn minus 2, then if this is positive, it will also be positive. In the same way, Sn minus 4, Sn minus 6 will also be positive. Then in that case, the sequence Sn minus Sn minus 2 will be greater than 0. That is, Sn will be greater than Sn minus 2 will be greater than Sn minus 4. The sequence will be monotonic increasing sequence. And if this expression is negative, then all the terms in the series, they'll be negative. So in that case, Sn minus Sn minus 2 will be less than 0. That means Sn will be less than Sn minus 2. Then in that case, this sequence will be monotonic decreasing sequence. Now, if we look at the sequence of other terms, which is Sn minus 1 and Sn minus 3, there is this minus sign. So that means this Sn minus 1 minus Sn minus 3, it will be negative when Sn minus Sn minus 2 it is positive. So in that case, it will be negative. That means Sn minus 1 will be less than Sn minus 3. In that case, the sequence will be monotonic decreasing. And for the second case, when this value is negative, then Sn minus 1 minus Sn minus 3 will be greater than 0. That is, Sn minus 1 will be greater than Sn minus 3. Then the sequence will be monotonic increasing sequence. The two subsequences of odd terms and even terms, they'll both be monotonic. And if sequence of odd is increasing, then sequence of even will be decreasing. Or if the sequence of odd is decreasing, then the sequence of even will be an increasing sequence. So we have proved that the sequence is bounded and the two subsequences of odd and even terms, they are monotone sequences. So if the sequence is bounded and monotone, then both the subsequences, they are convergent sequences. Now suppose sequence of odd, it converges to L1, and sequence of even, it converges to L2. Then from this condition we can write L1 equals S upon 1 plus L2 if n is odd, and will be L2 S upon 1 plus L1 if n is even. Now if we compare these two, we'll get L1 plus L1 L2 will be equal to L2 plus L1 L2. Now L1 L2 will cancel, so we'll get L1 is equal to L2. So both the subsequences, subsequence of odd terms and subsequence of even terms, they'll converge to the same limit, say L. Then the sequence will converge to this limit L, and we can write this L equals S upon 1 plus L, that is L square plus L minus S equals 0. So this limit point of the sequence, say L, it is a positive root of this equation, x square plus x minus S equals 0. And this is what we need to prove.